And hello, here's Mr. C. This is a recording to give you a short demo of how to do the sound laboratory. I'm not going to go too much into detail, but a little bit. Here are your instructions. You have the lab report, separate document, the virtual lab, and the procedure itself is basically to complete this table here and do some screenshots and document what a standing wave is, and then use the velocities that you're going to get for each of the three gas media, air, carbon dioxide, and helium, to do some calculations in the lab. So this is all here. And already I highlighted here, one thing is that you cannot get all the values for helium. We cannot excite that many standing waves, but do as many as you can. And I want to just show you first how to do it, and then we'll do a little bit, we'll fill in the table. Of course, I want to show you that. So the speed of sound, and I've done the lab, you can say no and then go through some training, but I want to demo it to you. Here it shows a picture of what we're going to do. It is what's called the Kundt tube, Kundts. He was the first one that did this type of experiment with pollen, and he was able to do standing waves, and there are other tubes out there. One is using fire, and it's always an exciting tube too, an exciting experiment too, and all kinds of resonance experiments are out there. All rely on standing waves. So let's enter the lab here. I use the yellow glove today, and we're going to see the setup here in a second. So here's our setup. I will say no to the demonstration. We have the media up there, so there's pollen inside the three glass tubes, and the glass tubes are filled with air, carbon dioxide, and helium. And we're going to grab one of these tubes, and we're going to place it in this resonance stand. So on the left side we have kind of a sound generator, and that's controlled by a frequency generator down here. And then we'll create a wave that propagates through this medium and gets reflected, and at certain frequencies it will create a standing wave, and that's what we want to measure. So we're going to measure with this ruler, but first, to turn it on, now we use air as an example. It would be nice to enter numbers, but we use that rotating lever here to increase the frequency. And at the beginning, just turn it and look at the pollen. And there was a little wiggle there. I hope you can see that. And we're going to go back to that one, of course. We'll increase the frequency. I keep turning. Here's something going on, right? Here's a standing wave, basically. If you keep going, and we're going to determine exactly the wavelength and the frequencies. There was another one. And you could be doing it on any of these, but we want to start from the beginning. So the first one we observe, we go back now all the way down here, is when we increased it at about, here we go, there's something going on here. We see there's a maximum on the right, there's a minimum on the left, so we have one node visible here. It turns out we can measure the length, but it's basically the length of the tube. But to demo that is, we would hold the ruler like below it, and then it will, close to it, it will lock. That's what I wanted to get to you. It will lock. I don't want to overlay it too much, so here we see it now. And so now it's locking, and you could zoom in. Let's zoom in for a second to see the measurement values. We have on the left side 0 centimeters, and it's not super, like, you don't need to worry about centimeters. And on the right side we have 100 centimeters or 1 meter, right? We could move it a little bit to the left. So the maximum, that's called the antinode, is 100 centimeters away from the minimum. And I'll go back now for this first resonance, and that's at 84 Hertz. We're going to put that in our spreadsheet. I'll put the table over there already, but I'm going to grab it one more time here. Can I get, I need to open a spreadsheet here. I want to show you how we record it. In the meantime, I'm going to grab that table here. And just grab it like we always do. Control copy here. Close that, and I have an Excel file here. I'm going to put that in here. Alright, so for our first node here, we had a frequency of 80 Hertz, and the first wavelength we want to calculate is lambda half. It turns out when we go from a node to an antinode, that distance is lambda fourth. So to get to lambda half, we need to multiply that lambda fourth by 2. So what we're going to write here is in meters, not 100 centimeters, we would write 1 meter for lambda fourth. So we would write 2.0 meters. And we can change, of course, the significant figures a little bit. What was it? Insert here? No. Home. And we'll change that one a little bit. Going the wrong direction, I think. All right. 200 would be good enough. I'm going to close this one here. Then we can, of course, calculate lambda, right? We can say, hey, if lambda half is 2, then lambda equals 2 times lambda half, right? And the velocity is meters per second, and hertz, of course, hertz represents 1 over second. So all we have to do is we're going to multiply the wavelength with the frequency. And we get about 320 meters per second. I think we learned in the class it's 333 or 330 meters per second, so pretty close. So now for the second resonance, we go back here and we keep increasing it. So the first one important again is from the, and we unlock it first, let me see if I can unlock it. From the node to the antinode, this was lambda fourth. And now we increase it and we try to determine the next frequency. There's nothing there, nothing there. Here was something. And you gotta have to do it yourself, so it's a bit tricky always. I want to go back. Here we go. All right. So now 256 hertz, and we could go from node, this is the minimum, to the next minimum, here to here, or you could measure antinode to antinode. It doesn't really matter. I would do node to node now. If I start on the left here, sometimes maxima are easier to see because the way it locks. So let's go maxima. Everything is just shifted. So now it locks. I could make out the minimum is about where this stand is, right? But if I write down the node here, and now I zoom in again, if I write down, I'm sorry, the antinode here, and that's about what, 32 centimeters, and go to the next maximum here at 90, let's be friends here, 99, so 32 to 99 centimeters, then it's equivalent to going between the nodes, right? If I go between, I'm locking here again, here, where my hand is now, and there, it's the same as if I go to maximum to maximum. So 32 was it to 99, and I'll put that in the table. Unlock it first. Okay, I got it. And 256 hertz. Let's go back here. So frequency is 256 hertz. So now to get to lambda half, I tend to use the extra cells here always to write down the values. So we had 0.32 meters to 0.99 meters, right? And that distance now is lambda half. So the distance between two nodes or distance between two antinodes is equal to lambda half. So it's a bit different from the first node. Equals, and I just need to say equals the big one minus the small one here. Okay, so 0.67 is lambda half. Well, lambda, I just can drag down these equations here. Lambda is twice that, and the velocity is 343 meters per second. I mean, it's not totally the same, but not too far off either, right? You're going to see much bigger differences between the gases, so I'm going to reduce that to 343. When later on you have to make calculations with the velocity of air, just take the average, calculate the average of all your nodes there. So the next ones I'll let you do those 3, 4, 5. So you're going to see more and higher frequencies. Let's just do one other gas. So you see that it works. We'll turn it off for that. Everything settles. Let's grab CO2 here. Place it in there. turn it on and we increase it, we'll just start from the beginning. There was already a wiggle. I saw it. I looked at the values, but I saw something moving up there. This is already a higher one, a higher order one. So this would be the n equals 1 at 205. Do a quick check here. N equals 0. Let's go back down to lower frequencies. Ah, here was something. I saw it very quickly moving here. About here, I would say, maybe a little bit lower, but 65 hertz. And again, by now you know already that the lowest node is basically the length of the tube. So at 65 hertz, we have a lambda of equal 2 meters. So we can go for that and just type that in here. So we would say this time at 65 hertz, we have a lambda of 2 meters. It's the same as before, and just want to copy these equations over. And there's a way to copy just the formulas, right? And so I get a don't send. There was a box here. Wavelength of 4 meters and a frequency and a velocity of 260 meters per second. So it's lower. And later on, you have to start interpreting why this is lower. So that probably needs some research, but you can also think of air is mostly nitrogen and oxygen. Carbon dioxide is a carbon and 2 oxygen atoms. So that molecule is much bigger than air, right? So velocity is there that relies on a medium, in our case gas molecules colliding, and those molecules being bigger, the velocity will get smaller. Well, guess what for helium? It will get larger. These velocities will be quite large, and that means you cannot excite all the nodes there, so you only can do a couple of, but you should definitely do that, and it should follow what it should be related to the size of these molecules. Helium being inert, smaller than air molecules, smaller than N2 or O2, and definitely smaller than CO2. There's a question in the lab that you have to answer for that. So the lab itself, not too hard. If you and again, I would just write down here the various sizes of the maxima and then copy the equations over. That should go straightforward, and they should all be in the same ballpark and significantly different from each other. Like I said, if it comes to some sort of calculations, you always that you have to do some sort of calculations, you can always do the average of, and you select all the values here, and you use that one. You can round it, right, and use correct sig figs here, please. Then hop over briefly to the lab report. Oh, I want to point out some things there. I just need to make it fit here. Oh, it fits well. So the first work of 14 points is to take a screenshot. Take of the air-filled tube a screenshot of any of the n equals 2 to 5 waves, and I want you to label the nodes and antinodes. So paste it in a paint program, or do it even here. You can add a text box. Show me where the nodes are and the antinodes. Again, nodes they are where there's no excitement, basically at the minima, and antinodes are on the top. And then you explain me how a standing wave occurs, right? Constructive interference, that's the key term. So here's where you're going to put the screenshot. Here's where you cut and paste all the data in here. And then a short answer about standing waves. In the second part, you're going to tell me actually what the velocities are. So take the averages there and tell me, hey, the velocity of air is so many meters per second. Helium, should have flipped it around. Carbon dioxide, then helium, right? So show your data. I mean, write it down. Which is the fastest, and explain why do sound waves travel at different speeds in each gas, right? And I gave you a hint already. It has to do with the sizes of the molecules. And then down here, you use, let's say a sound wave has a certain wavelength, and that goes through air, helium, and carbon dioxide. And then you need to find me the pitch. Well, the pitch is the frequency. So you just flip the equation around. This time you calculate the frequency, and you use the velocity, and you divide it by the wavelength. Okay, that way you find the frequency of each medium, and so you can do these calculations with the average of your measurements, right? The average velocity, and you can find me those. And you definitely can see then that the frequency of in helium will be much higher. And I hope you have experienced, or at least seen it on TV, where if someone breathes in a little helium, they're gonna talk a little funny, like Mickey Mouse, or like a Class Connect session that is buffering, right? And I hope you understand now why. Um, and that's the short demo of this lab. It's called Kanztube again, and it's quite nice setup. It would be tough to do it. Certainly you can Google Kanztube resonance. I have one actually here. Oh, I forgot that I can't send it to you, but you can certainly, let me see if I can bring it up here. Yeah, there's someone doing a Kanztube experiment. A real one. So you can do it with an enormous effort. Here's a resonance, right? Two minima. You see two nodes here, and he measured the frequency, or he knows the frequency he's exciting it for. It's a bit noisy. You hear the deep sound, and yeah, you can find many of these demos on YouTube. Now he's cranking up the sound. He excites 1, 2, 3 nodes. Okay, so I hope you have fun with that experiment, and I'm looking forward to seeing your data, and let me know if you have any questions. Thank you for watching.